Okay, we are going to go ahead. Welcome back for hour 2. And we have Mr. Gregory Hutto. He is a wing operations analyst for the 96th Test Wing. He's responsible for embedding designed experiments as the principal test method for hundreds of tests each year. He teaches an extensive series of short courses and test methods to all testers from the wing commander to our 520 scientists and engineers. As a lieutenant colonel in the U.S. Air Force Reserves, he served as a senior military advisor to the AF Operational Test and Evaluation Center Test Support Director, and as a special advisor for test design to the Air Force Flight Test Center commander at Edwards Air Force Base in California. Mr. Hutto is a distinguished graduate of the U.S. Naval Academy in Operations Research and holds a master's in the same field from Stanford University. Over the past 30 years, he has served in nearly every branch of test and evaluation, from laboratory basic science to joint operational field testing. He would like to publicly repent of his 11 years of testing without the benefits of the principles of well-designed experiments. That's an awesome resume. Greg, we would like to welcome you. You have the floor.
Sherry, thanks so much. Always a joy to talk about my favorite subject, experimental design, and particularly in this audience here, one of my favorite pieces of software. I've been using Design Expert since, golly, back in the 90s when you still had Design Ease and Design Expert, and been using it pretty much full time since about 2007, 2008, when my colleague, Dr. Jim Simpson, introduced that to me. I'm also going to be a warm-up talk now for one of my other favorite experimenters, Dr. Drew Landman, so be sure and stay tuned to his electronic vertical takeoff and landing talk next. I certainly will. All right, so today what I'd like to do, and by the way, that's not an accurate picture of me. My hair is a little bit grayer and I've got a little bit more of it, and better legs. But anyway, what I wanted to talk about today was some of the tricks that we have played on our software in order to accommodate the endlessly challenging physical details of applying experimental design to the world of flight test. So I've, out of thousands and thousands of examples that we've done, I've chosen 3 to talk about today to illustrate some of those tricks, and also the really wonderful capabilities that Design Expert has in supporting customizing your design. So hopefully we'll get through some of that today, and I look forward to responding to any of your questions here. So moving forward. There we go. That's just part of the slides. There's me. There's an abstract, and it's moving into the fall down here. Temperatures moved into the 60s at night, so that's really welcome down here in sunny Northwest Florida. But as we approach the Christmas season, I always love to read this little piece of absolutely beautiful prose. Yes, Virginia, there is a Santa Claus, and I would echo that to keep the magic and enchantment in childhood, there really is a tooth fairy. So I had many years of experience with that with my children. All right, so a little bit about Eglin Air Force Base. We're up here in Northwest Florida. We refer to the peninsula as Florida. We're in the a little bit more reasonably minded part of the panhandle here. Eglin Air Force Base is the largest temperate tropical test base in the world. We're about 20 miles north to south and 40 miles east to west in our land range. Fort Walton Beach in Niceville and Valparaiso. Yep. It really is called Niceville, and Destin, Florida are right down here. And our land ranges occupy that portion of the peninsula. And then we've got about 125,000 square miles of airspace over the Gulf that we're increasingly needing to use for some of our long range weapons. You've probably heard about our hypersonic weapons and so on and so forth. There's a CV-22 Osprey flying along our beautiful beaches. This is Destin here. And in fact, my in-laws have a condo about right there where I'm pointing with my cursor right now. Anyway, but we are growing in our experimental design practice, and I sure would like to see resumes from any great experimentalists or enthusiastic ones that would like to come join us. My emails are on the first page of the slide, so feel free to contact me if you'd like to come join us in military test and evaluation. And the Air Force does some pretty good work in operations research. A few years ago in 2017, not very long ago at all, we won kind of the Nobel Prize of operations research. You may be aware there is no Nobel Prize for mathematics, surprisingly. But we won the Informs Operations Research Prize that year, actually tied with Walt Disney World for the organization with the greatest practice of operations research. Our three proof cases for our good work in OR included the work that myself and my colleagues have been doing in design of experiments. So it's pretty well known, and it's really high caliber. So please come join us. All right, you may know this is one of my favorite stories about experimental design. It all started really with beer in the 1890s, believe it or not. The Guinness brothers decided to convert their Guinness brewery from brewing as an art to brewing as a science. And so they went around and they hired the best chemists and mathematicians they could get their hands on. They brought them in, put them all in the same house. They all lived together, kind of a frat house there. And they took those chemists and they made them brewers. They spent about 2 years apprenticing them to master brewers. And then they became themselves craft brewers. And each one was given a little microbrewery and set to work to do the experiments. So William Seeley Gossett was a particularly energetic young chemist. And as he began to do his brewing experiments, he recognized he had a fundamental problem in test. And that is, okay, I've got this new brew, we'll call it stout, new stout, and I've got old stout, and now I brew up a couple of batches of each. How do I decide which one's better? I recognize that I have run-to-run variation. How do I know when that variation, that difference between the old and new is large enough that it's not just a product of random variation, but in fact is based in cause and effect? And so he went around and he talked to all the great statisticians of the day, including a gentleman named Carl Pearson. And Carl said, it's easy. Just collect thousands of gallons and you won't have to worry about that experimental error. And Gossett went away sad because obviously that's not a practical answer. And so he began to use literally drawing figures on pieces of cardboard and drawing random samples of size 4 from those pieces of cardboard where he knew the population mean and standard deviation, and began to try to estimate that population mean and standard deviation in small samples. And he wrote a paper called The Probable Error of a Mean, which forms the basis for our t-test, and got Ronald Almeyer Fisher all excited as an undergraduate at Cambridge about experimental design. And so Fisher came along a little bit later and extended the t-test into ANOVA and regression the way we love it today. But it all started with beer. Okay, so for my first case today, I'd like to talk about a single engine climb case. So the idea here is that for safety's sake, whenever I have an aircraft with more than one engine, I have to do this calculation. And by the way, for all my examples today, I'm going to be kind of masking the actual system that we used. It's not that those are classified, but we have some fairly thorough restrictions on public release. So I'm making all these as generic as I can for this presentation. So anyway, so every aircraft with more than one engine has to calculate whether if they lose an engine during takeoff, can they actually safely climb to the pattern altitude to the point where they can turn around and land again. And you may remember that Sully aircraft where he lost both engines and had to land in the Hudson. So this isn't that case, but if you lost one of the two engines, can you climb? And that's a function of the aircraft gross weight. It's a function of the air density on the day. At higher altitudes, harder to climb. It's a function of the drag of the aircraft, and so on and so forth. So there's several things that impact the ability for the aircraft to climb with a single engine. So what we wanted to do was vary those conditions, look at the single engine climb rate, and make sure that it was greater than some really minimal value like 150 feet per minute. So here's an input process output diagram. By the way, that's a B-25, not the aircraft that we use for this test, but it is a wonderful little aircraft, one that we is near and dear to our hearts down here at Eglin. It was the aircraft that Jimmy Doolittle and his Raiders rode to bomb Tokyo off the deck of two carriers in April of 1942. We just lost the last member of the Doolittle Raiders. He died this year, the 9th of April at 103 years old. But the Raiders used to come down here at Eglin where they trained for that little exploit every year. And Dick Cole left us this year and went on to join the rest of the Raiders. Anyway, so here's the input process output diagram. We have pressure altitude, the aircraft gross weight, gear setting up or down, flaps, and outside air temperature. And then the output is the climb. And of course, we want to compare that climb rate versus the charted value there. So this is what we, and let me tell you about some of the challenges then. Okay, so white line number one is gross weight in an aircraft. For the most part, is primarily a function of fuel. Now they carry bombs and weapons and those kind of things, but by and large, a large part of the aircraft weight is a function of fuel. And so when we're trying to set the gross weight for these climb rates, we can't obviously ever have 100% fuel because you need some to take off and climb. You can't ever be at 0% fuel because obviously then the engines stop and you have a crash. So all of our points had to be between the extremes, but just as Martin showed us, the factorials, d-optimals and other factorials love the edges and the corner of the design space. So how do we handle that since we will never be at the edges and corners really for any of our runs, and in fact most of our runs will have to be in the interior. So we tried building optimal polynomial. We tried to use discrete numeric as an approach for gross weight, and then finally we hit on the idea of building the design using gross weight, which is truly numeric, treated as categoric, 3 or 4 or 5 level categoric, to get a balanced number of interior points. So that was one of the first times that we've had recourse to this trick that will give you a balanced number of interior points. And then once you build it as categoric, you can always go back and use design experts' capabilities to convert the column to numeric and then evaluate the design you got with the truly numeric X variable. Maybe we'll be able to take a look at that here, but let me continue on with some of the other challenges with this. The second challenge is, and this hopefully will not come as a surprise to you, as you go up in altitude, the temperature goes down up to a certain point, at least in the atmosphere. Certainly in most of the places where we fly in the atmosphere, it gets colder as you climb. And so this test was to be done in August here at Eglin. And the coldest temperature we ever have is around dawn, and that may be around 70 degrees Fahrenheit. And then typically during the day, it might get up to 90, 95 degrees during the day. But as we increase in altitude from our altitude here at all of 60 feet above sea level up to 5,000 or 6,000 feet above sea level, we have a standard temperature lapse rate of about 3 degrees per 1,000 feet. And so it's not that we can't, the 95 degrees at 5,000 feet is a difficult point. It's a point that doesn't exist. And so none of these points here exist. And similarly, these points over here do not exist. And so we're driven to having a design that leans to the left here. And I'll talk a little bit more about that as we go forward. So what this does, it correlates density altitude with its two components, pressure altitude and outside air temperature. So we tried all kinds of different attempts to generate a balanced and constrained optimal design that obeyed these constraints with a number of interior points. We had to pay attention to the variance inflation factor, or the correlation of temperature times altitude interaction. And we even went so far as to build this design with a fewer number of points, say around 30, and then augment it with 4 to 8 points with the augmentation optimal factorial augmentation tool to try to build up and strengthen the temperature by altitude interaction. So I must have built, I don't know, 15 designs like that to try to get that to work. All right, so that was white line number 2. And then white line number 3 is, and here's a B-25 taken off from a hangar deck. On the deck of a carrier. You can see the flaps are down for short field takeoff, and of course the gear is down. So this is very commonly a configuration for takeoff. But in the design itself, for the particular aircraft we were dealing with, they like to have the flaps either at 0 or 30 degrees. They didn't like to have any intervening point. And then the gear is either going to be completely up or completely down. No partially raised or lowered gear is allowed. So treating these things, which again are in native numeric, treating them as numeric, discrete, and categoric were various tricks that we played. So a real challenging test. Let me go on and show you how we finally solved it. The final design was a Rube Goldberg design. We went back to a face-centered central composite design after we tried all kinds of optimal designs here. We built and then defaced a face-centered central composite design. We manually adjusted the temperature and the altitude to obey the temperature lapse rate. We went ahead and it just accepted the fact that we're going to have multiple gross weights and temperature settings as set point errors. We manually moved the center point values of gear and flaps out to the edges to make them kind of pseudo centers. And then finally, there were several unsafe combinations that we had to manually adjust. We take those unsafe points and move them up or move them over. So that was the final Rube Goldberg design we built to solve this problem. The test engineer was not very honest with me. He told me that we would only be able to afford 36 points, and then he actually flew 81. And so that kind of irritated me, because building this whole design with only 36 points was one of the chief challenges. All right, so here's the face center central composite design with all the adjustments that have been made to it. And you can see we had some slight elevation of the variance inflation factor. This is altitude, and this is temperature, and this is the altitude temperature combination here, the AB interaction. And of course, we have, when we fully stuff the model here with all of the model terms, this is a quadratic model shown here. We typically have a kind of inflated variance inflation factors that we don't typically get when we reduce the model to the actually active terms. Here's the Pearson R for the fully stuffed model, and you can see some points here, especially the AB interaction. Here's the one, the Pearson R for the 81 run design as executed, and here's the variance inflation factor, which I would admit is kind of alarmingly high for the AB interaction, but God had a sense of humor, because what happened when we actually went to execute this design is all of our high temperature afternoon sorties were canceled due to the thunderstorms that we typically have here around Eglin in the afternoon in the summer. And so it really correlated temperature and pressure altitude here, but we were still able to drag out the results and get the information that we needed, which was that with the gear down, the climb chart was accurate, but when the gear was raised, the climb chart was not accurate. And here's an example of the actual design as executed. Here's the pressure altitude versus temperature. You can see that leaning over there to obey the temperature lapse rate. The pilots hit the altitudes reasonably well. They were very unkind and had gross weights all across the map. We had pressure altitude versus gross weight. The low altitude, high gross weight was eliminated for unsafe. So was gear down at low altitude. Those points were eliminated or moved over as unsafe. So anyway, here's a design as we actually executed it. Lots of set point error with temperature and gross weight, but we got a pretty outstanding result. For the most part, the points down here below this blue line were safe. The points above the blue line were less safe, less conservative in their climb rates, and we identified those as being the gear up situations. So that's example number one. Moving on to example number two, we had a bomb that we were testing down here, a new weapon. Again, this is not the actual weapon. It wasn't the Wile E. Coyote, but what we built is what we refer to as a couple of Franken designs. We take several designs with different objectives and combine them together into a single design. So here's the problem with that. We had, this is velocity or Mach down here on the x-axis, altitude on the y-axis. The blue outline here was the release envelope for this weapon. So we needed to fit points within this. We had about 26 points to play with. We had several partners that had each their own weapons to add to this mix. So we had to convince our partners to join with us to build experimental designs here. We had a pretty good idea how this weapon was going to behave, and in fact, it turned out to do exactly what we predicted it to do. So what we did the early on, this was, I don't know, 11, 12 years ago, we built a menu of 8 different designs using Design Expert, each with their own pros and cons, and then objectively graded each one of those and presented the program office with our recommendations. So here was kind of our report card. In the columns here are various designs. Here's 8 different designs. I'll zoom in on that on the next page. Here's our metrics of a well-designed experiment in the columns, and then they're color-coded because this probably happens in industry, but it certainly happens in the military. As soon as you become a high-ranking officer, a colonel or above, you lose your ability to process numbers, and everything has to be boiled down to what we call stoplight charts, red, yellow, and green, with the obvious meaning of dark green is really good, dark red is really bad, yellow is caution. And so we went ahead and color coded these numerics here so that our senior officers and senior civil servants could make their choices. So to zoom in on that report card, these are some of the metrics that we use. And again, one of the real strengths of Design Expert is that it has a really super menu of design metrics that one can look at to evaluate the goodness of their design. And for all three problems that I'm talking about today, we relied on those metrics heavily. So we look at the name of the designs. Here's a Taguchi design, and those are well deserved, resting on the ash heap of history. You can see not so good performance there, especially when it gets to interactions. There's a face-centered central composite design, a small composite design, an I optimal two-factor interaction model, a D optimal two-factor interaction model. One of our favorite designs, the 2 to the K fractions. This is a 2 to the 5 half fraction. This is a 2 to the 6 quarter fraction. And then just to show off, here's an I optimal quadratic model. So a number of factors there, levels for each of the factors, number of responses, are they real valued, are they objective, number of test events, savings, and so on and so forth. It goes down to power for the various model terms, talk about some execution issues here, especially the value of having true replicates for measuring pure error, and then for the analysis portion, the type of prediction model that's supported, and so on and so forth. So even my daughter, who was an anthropology major, was very easy to look at this chart here and see the designs that really recommend themselves are the good old-fashioned 2 to the K fractional factorials here, and they're well deserved because of the really great performance we get with these design metrics. So on to some of our tricks that we played on our software. First, we had a fast running simulation. Could be run either in Monte Carlo fashion with some variation or in pure physics mode. But what we did, as Martin mentioned here, is we used two designs and actually stitched them together. We built a D-optimal polynomial design that very well populated the corner and the intermediate values. So we did a 5-level D-optimal design here across 58 variables, which is a personal record for me, by the way. And then we augmented that with a space filling design for those same 58 variables to make sure we didn't miss any tricks. This was a fast running simulation, so a 2500 run design was really no trick. They could get that done in just an hour or two. So we did 6 or 8 sets of this size over the range of the control noise variables. This was doing digital engineering before digital engineering was cool. This was, I don't know, about 5 or 6 years ago. Here's the input process output for the bomb drop. So pressure out to velocity of the aircraft, climb or dive angle of the aircraft, range to the target, handoff errors from the aircraft, position X, Y, and Z, plus velocity errors because the aircraft doesn't exactly know where it is and how fast it's going to hand it off to the weapon, type of aircraft, and then downrange and cross range from the target in the various launch regions there. And then just the simplest one, the miss distance from the aim point was our output. And again, this I will stress is not the actual bomb under test. So we can't fit a traditional design. This is Dr. Jim Simpson and Dr. Drew Landman's embedded face-centered central composite design that you can see hiding out over here. Really doesn't fit within these constrained regions. We have these kind of weird looking constraints here, a little notch, little bump out there and then can't go above this altitude. This is too fast Mach. As we go down in the atmosphere, if you maintain this Mach number, the wings come off of the aircraft, so that's not popular with pilots. We wouldn't do a level release below this altitude. Our loft, this is where we pull up and toss the bomb by pulling the nose of the aircraft and pulling about a 4G pull, so the bomb comes off and flies a longer ballistic trajectory than you'd get otherwise. These were all level releases up here, all loft releases down here. So how in the world do you build a design to fit within those constrained regions? It was a real challenge for us. And oh, by the way, we don't really think we're going to do that many high-speed, high-altitude loft releases. Most all of them are probably going to be level. So I didn't really want half of my runs to be lofts and half of them level. So a lot of challenges in building this design. Here's the way we lied to our software. So we told them white lie number one, just build us this one set. So what we wanted to do was use a well-schooled candidate set. And what we actually did was we built two candidate sets. So we made sure that the variables were in common. They had different ranges, but we want to make sure the same variables were in there. We wanted a large level design and a very large loft design. And then we took the level and loft design and combined those. And when we combine those two designs, then the points will obey all the constraints. So let me see if I can bring that up. I think I have that one. There it is. And let me bring that over on this screen. So here's a design expert with the combined candidate set. You can see the points down here at the lower altitude and at medium to high Mach. These were all different loft numbers. These up here were all level deliveries. So combining the the loft down here with the level deliveries, that gave us a really good candidate set that obeyed all the constraints. And then we constructed optimal designs from this merged candidate set. So that was white lie number one. We actually needed two sets and we combined them into a combined candidate set. So white lie number two then was I'm going to do this in 4 blocks, please. So we only get a total of about 26 deliveries for this bomb, and we only want a few of the lofts. So we don't want 26, divide that by 2, 13 lofts out of the 26. I only want a handful of lofts, say 4 or 5 or 6. But I don't want just 1 or 2, which would constitute just a demo. So here's the way we handled that. We built our master design in 4 blocks of 36 runs. And then since the block is orthogonal to the design, the two-factor interaction in this case, we can discard the loft runs in the later blocks. And that trims our number of runs from 36 down to about 26. And therefore, the loft model will be mostly orthogonal to the blocks, and the loft model will be supported in block 1 and block 2, even though we've damaged the loft model in blocks 3 and 4. And again, careful attention to the metrics and they didn't suffer that much. So we ended up with 26 runs with only about 5 or 6 loft deliveries. Okay, moving on to white lie number 3. I'm going to deliver all 26 points. Well, the program office told us, it'd sure be nice that if we have some reliability failures in the first 20 runs or so, could we scavenge the last few runs of your design as mulligans or do-overs? So let's say run number 10, the weapon came off and had a reliability failure. It didn't guide at all. So we certainly don't want to combine a non-guided weapon with a guided weapon to calculate the average accuracy. So those need to be replaced with weapons that were performing, and they didn't want to go over their 26 point budget. And they said, can we set it up so that the last runs are the least valuable and can be used for mulligans? So again, we use another clever trick here. We built this full set by augmentation. The first 8 runs we built to support the main effects model. We then went runs 9 to 19 for the likely 2-factor interaction model. Remember, we peaked using the simulation, so we had a really good idea what this the output model is going to look like with a few quadratic effects. So we augmented the main effects to a 2-factor interaction model plus a couple of quadratics. So by run 21, the likely model is well supported. And when we support these by leverage, when we sort the design by leverage, then that made 20, 22, 23, 24, 25, and 26. Those last 5 runs could in fact have been used to replace reliability failures in the earlier runs in the design. As a result, let's see. So here's a design that we ended up building. The dark blue and the light blue are our design points. The dark blue were the level deliveries. The light blue were the loft deliveries. We had one of our other partners, the operational test center, did all of these right in the heart of the delivery envelope where they thought would most likely it was going to be used. And then we had another partner that wanted to check out the very edges of the envelope, and so they did these kind of orange yellow points here out in the very edge. But all of those were combined to get a really accurate performance estimate for this weapon. And for the first time and only time in my career, we stopped at the end of 21 runs. This weapon was performing so well and so much in accord with our expectations that they actually gave up their last 5 runs, turned them back in, and completed the test 3 months ahead of schedule and turned it over to the operational users. So a really great success story using combined Franken designs and the capabilities of Design Expert. Okay, so I'm pretty much on track here for finishing on time. Third one is my baby. I'm kind of very pleased with this. I've been banging my head against this problem for, oh golly, 15, 16 years now. It's the problem of target location error. All of our weapons now pretty much have the capability of homing in on coordinates on planet Earth. So if you give me the latitude, longitude, and elevation of a target, then I can put a weapon on it. Basically night, weather, doesn't really matter. I can have my weapon fly to those coordinates. And so we have all kinds of sensors on board our platforms, plus other sensors that are on the ground and in space to find these target coordinates and the target coordinate error for our sensors. This is a little picture of one of our targeting devices. So moving along here. Estimating target latitude, longitude, and elevation is a frequent problem across the Department of Defense and especially for the air and space forces. The target battle space of all the different conditions under which we might want to estimate target location is very, very large with many variables. The response variable, the error in our target coordinates, is skew with inconveniently increasing variance. So we have a heteroscedastic response variable. And then finally, we have some pretty extreme restrictions on randomizing our execution order because you may have noticed this, we have not, even though our space forces have the Star Trek symbol for their service symbol now, we don't have the Star Trek transporter yet. And so we have to actually occupy the space as we fly back and forth across the sky. We can't just ping pong around there and gather data in any point that we like. And using Fisher's gold standard of randomization runs, we excessively violate that one in the spirit of split plot designs, which again, hats off to Design Expert for how well they do that. All right, so target coordinates problem, difficult. This is kind of an idea. This is a range down here, ground range. This is altitude here in the vertical axis. We can look at the physics of the problem, and we're taking target coordinates on the surface of a sphere. The sphere increases, and the surface area increases as 4 pi r squared. We may remember that from high school geometry. And so we know we've got a quadratic response model, and we also have a skew and non-constant variance response variable. And then to add to the top of that, we have to estimate the 90th percentile, and so we have to use one of the variants on the generalized linear model called a parametric survival model by the work of a guy named Bill Meeker to estimate the 90th percentile target location error. But I'm not going to discuss that today. I'm going to talk more about the challenges of building these designs for target location error. All right, moving along. Okay, so here's the input process output diagram for the sensor target location error problem. On the left-hand side, we have the altitude for the sensor, ground range, angle off the nose. We don't look straight ahead. We can look off to the sides and even backwards. What kind of sensor we're using. I could add radar to this as well. What kind of target type we're looking at. The accuracy does depend on some of the target characteristics, which side of the aircraft, and then finally, am I heading toward the target or away from it with this set of input variables. Oh, and here's the error, the actual versus the measured location. There's a whole bunch of unique points, at least 600 or 700. So we obviously are going to need a fractional design. One trouble with building these fractional designs, though, is that, oh, and before I get into the fractional designs, let me show you one other thing. Which coordinate system should we use? So we could use the Cartesian coordinates, X and Y, so Y-axis of altitude, X-axis of ground range, and fly back and forth like this. Or we could use the polar coordinates here, where we're using basically R theta and phi for azimuth, elevation, and slant range. And it may seem that the polar coordinates are more natural for this problem. You can build a face-centered central composite design inside there very, very nicely. But in any case, we have to traverse the space in between these points, so don't forget that. Here's the design in Cartesian coordinates. It's basically a trimmed down here. We're at very low grazing angles far away from the target, so the coordinates are really bad. No real reason to take them down here. They're too bad to actually be useful. When we plot the flyable points in polar, we see that we have a pretty good correlation between the depression angle and the slant range. And so really the polar model has too much of a variance inflation factor to really make it useful. So, and I can't get the pilots to fly at 80,000 feet to populate that whole polar region. So as a practical matter, the Cartesian model is our best choice. So moving forward, here's one of the problems with the fractional design. When I build a fractional design, almost no matter how I build it, using a factorial, using an optimal design, using a response surface design, I end up leaving holes. And so as I fly inbound here, and then over in this panel, outbound over here, I end up telling the pilot, take that point, oops, skip one, take that point, come down here, take it, skip it, and so on and so forth. So leaving all these holes in the design region really doesn't make any sense, besides making us look kind of dumb. So don't like to look dumb to our pilots. So how do we cover all of these points, because we've got to be there anyway, so we might as well take the point while we're flying through that space? And how should we set the other variables that aren't just altitude, range, and inbound, outbound? So we worked on this for years, and usually ended up crafting something by hand that we had to evaluate the design capabilities for. So Here's the solution that I came up with. And again, I'm kind of proud of this. What we do is we break the design into two pieces, kind of using that Franken design problem I talked about before. On the one, we do a full factorial of the what I call the geometric variables. All right, so I start up here at a high altitude, I fly in, I drop back, I'd fly back out, I drop down, I fly in, I fly out, I drop down, I fly in, and then I fly out again. That's one set of about 32 total inbound, outbound geometric points. Then what do I do with the other modal points, like side of the aircraft, angle on the nose, what kind of spectrum I'm using for my sensor, what kind of target I'm using on the ground. So the way I handle that is I build full factorials in the geometric variables, and then I take the modal variables that and again, we can have any number of these, 3, 4, 5, and we can have any number of levels, and I break them into blocks. So here's a 1, 2, 3, 4 variable design in 2 levels each. You're very familiar with the 2 to the 4th full factorial uh, uh, design, and I break that into 4 blocks of size 4 each. And Design Expert knows how to do this very well. And then what I do is I'll take block 1 and roll it against the first part of um, first part of my geometric variables. I'll take block 2, roll it against the second part of my geometric variables, block 3 against the next part, and so on and so forth. So I roll these blocks across the geometric variables, and I use a convenient block size so that it fits nicely into the replicates that I have for my geometric variables. So I call this a cross blocks design. Um, and the way it looks in Excel, and I'll bring that up here in a second. Here's my geometric variables, and I just happen to have this in depression, angle, and slant range, or polar coordinates. This is flying in, flying out, flying in, flying out. And then over here, you can see my modal design broken down in blocks. So I've got a 16 run design here. I run block 1 for the first 4, block 2 for the next 4, block 3 for the next 4, block 4 for the next 4. Now I'm about halfway through my my geometric variables over here. Then I'm going to go back and rerun the blocks starting with 2. So I start with 2 here for this one, 3, 4, back to 1. Then I'll do it again. This, by the way, is one full replicate of my geometric variables. Now I'll go back in, starting again with block 3, and run 3, 4, 1, 2, and so on and so forth. So this is kind of the Latin square pattern. If you remember Latin squares, nobody uses those anymore, but they do exist out there. And so we roll our blocks across our geometric replicates. And when we change, when we go to the next replicate, we change our block generators. All right, so when I evaluate this is a full 2FI model. We have some mild VIF inflation, mild 2FI and RSM covariances in the Pearson R correlation. We've flown these now for about 3 or 4 years. The models conform to the physics, and they cross-validate very nicely. So it's cool to see Design Expert's going to have some cross-validation capabilities in there in the future. All right, so not bad to believe in the tooth fairy, and not bad to lie to your software. In the physical world of flight tests, we have endless challenges to our creativity, and one of the things I love about Design Expert, it's a great partner tool. It gives me the capability to implement some of our clever dodges to meet the realities of flight tests. Okay, so finishing this up, I really encourage people to experiment with your experiment. Another great thing about Design Expert is I can simulate the response variable, so I not only can play around with my design, but I can play around with my analyses before I collect the first observation. And that is a great habit to get into. You'll always conduct dry runs. Either you'll do it before your experiment, or your first few experimental runs will constitute your dry run. So use Design Expert's capability to experiment with your experiment. Classical designs are already variance optimal. Check one of the classical designs before going optimal. I learned that lesson the hard way with the single engine climb. The best design turned out to be a manually mauled face center central composite design, and they can sure take a beating without really damaging the design metrics greatly. Candidate sets can hold several constraints at once. That's a real strength of Design Expert, being able to build up these candidate sets for all of our constraints. And oh, by the way, here's something that took us 5 years to learn. When you build those candidate sets, be careful of the model you ask it to draw the candidate set values from, because if you include an interaction for one of the corners that you've disallowed, if you have that interaction in the model, Design Expert will carefully put some points back into your candidate set for those corner points. So be careful about that. But the candidate sets are a great tool. A design block is a nearly orthogonal fraction to your model. So you can play around with using not all the blocks, or just a few blocks, or damaging a few of your blocks with a couple of really strong blocks. That's something you could think about. And then finally, if the physical circumstances force some sort of design order on you, remember the split plot rules, which are replicate the whole plots as much as you can stand and a little bit more. And then finally, take the design God gives you and roll the blocks across it. And that's turned out to be a really good solution to a problem I wrestled with for years. And we wouldn't do justice to talk about design of experiments without letting Ronald Almeyer Fisher have his say. One of my favorite quotes, and he's got a bunch of them. That's not an it's not an experiment, sir. That's an experience. But he calls to call in the statistician after the experiment was performed is like asking him to perform a post-mortem. He may be able to say what the experiment died of. All right, I'm at 48 minutes. I'm done, and I'll take any questions.
Perfect. Thank you, Greg. That was just a very enjoyable presentation. So I invite anybody who has questions to type them into the question pane at this time. We have one kind of question on the team/recruiting side of things from Gregory Perrine, who's one of our speakers for tomorrow. He wants to know if your team has ever collaborated with or recruited from the STAT Center of Excellence from the Air Force Institute of Technology. You worked with them?
We created the STAT Center of Excellence. We politicked to have the STAT Center of Excellence down here at Eglin in the 2008-2009, but the rest of the services and the rest of the Air Force wanted to give it to somebody more, quote, neutral, and that's how it ended up at AFIT. So yeah, we know the STAT Center of Excellence, Dr. Honor and Dr. Thor Thorson. I know them all very well. So yeah, we work with them regularly.
Very good. I am not seeing other questions come in at this point, so.
Surely there's got to be a couple of questions out there. This is hard when you're doing these things virtually. I can't see your faces, and so I can't see the frownies that I'm sure are out there. This was a lot of material that I ran through very quickly. We got 5 minutes left. So please, there's got to be a question or two out there. Did you understand the Franken design? Did you understand the multiple design candidate sets? I'd be happy to show you some of the mouseology of how those things are built. Anything I can help folks with. We got another 5 minutes.
Okay, let's see. From Michael Morrow, you emphasized BIFs a lot for your designs. I understand the importance for C/E interpretation. Your goals seem to be prediction. Is VIF important when you're most interested in prediction?
Well, that's a great question. So the variance inflation factor is very, very aptly named, right? It is a excuse me. It's one of the really great pre-test metrics we can use to diagnose the problems in our design. And when they say the VIF is 2, it's not something that one ought to lightly ignore, because the inflation of the variance translates directly into the inflation of our prediction errors and our confidence intervals. So even if we're just characterizing and not worrying so much about predicting, I always take inflation of the variance inflation factors very, very seriously. The second thing it does, you'll notice that the high VIF model terms have low power, and I'm an absolute power fanatic, because power answers the question: when I change X, what's the likelihood that I'll be able to correctly detect what X does on the response? And if you have low power, it's almost not worth doing the experiment. So a high VIF and low power go together, and I'm absolutely against a low power experiment if we can possibly find a way to improve it. So yep, and again, design experts got just really great diagnostic tools to look at the variance covariance among the model terms, the variance inflation factors, and statistical power. Just absolutely love that, being able to have a really good idea how your design's going to perform before you take it out of the barn.
Great. Okay, so Wolfgang from Germany wants to know where can I read more about Franken designs? So was that is that a specific design, or is that a name that you kind of made up to illustrate this Frankenstein concept?
Yes, exactly. We put it
Yeah,
together from body parts, right? So
yeah, yeah.
we've got a whole bunch of little clever things we've done down here that I really should publish and get in the literature. So I'd have to say I don't think, no, none of my published papers have anything about that, but I'd be happy if you want to send me an email. I'll be happy to. I've got some conference papers that we've done
Mm,
that I could send along, or I could send along some examples. But the basic idea is you have a couple of sound designs in their own right, especially the thing that Martin was talking about of when you're doing computer experiments using optimal polynomial designs plus space filling designs. It's a win-win. You get good modeling as well as space filling to find any quirks in your physics software. So I think that putting those two together into a Franken design, and the polynomial design is probably 10% of the size of the space filling design. At least that's been our experience when we do
sure.
15, 20, 30, 40 experimental variables. Really, really great approach.
Awesome. Well, if you're willing, Greg, to use the chat window and put your email address in, then maybe some people will send you some questions and you can have some more discussion with them on that type of thing.
Well, I got my email address on the first slide there.
Yeah, that
Let's see.
that works too. If you want to flip to the first slide, and then I'll need to start getting set up for our
Yep.
next presenter.
There we go. All right. I'll leave that up. All right. Thank you all. Great time and great piece of software. I can't endorse it because I'm a civil servant, but so I'm carefully not endorsing it. So I've got that on the record here.